Okay. Okay. Good. Good evening, everyone. I'm Manish Adhikari. I'm the group leader of Group One for the presentation of our group of IT 448 Introduction to Machine Learning. And today we are going to present our work for this project for in our group. Without further ado, let's start, and I'm going to share my screen. And Baxter, please, give me permission to share my screen, please. Okay, allow me to share your screen, please. Yeah, one of us should share our screen, please. So it looks like a lot of you have accepted our invitation to. So welcome everybody to for and we're happy to be welcoming you here. Slide.
It's on the top right. It's on the top right. Beside the Google Meet symbol.
Okay, slideshow. Okay.
Yeah.
It has been already recorded. Okay. So here is our project that we call it the project water characteristics, and the project has been done by the five of us: Manish, Subramanyam, Sai Krishna, Venkat, Jaswant, Bhaskar, and Ashok. So we are the group members here, and this is our presentation for our topic. Next slide, please. So we'll now talk about what is the background of this project. The background, the reason and why we are doing this project. This is for the prediction of the characteristics of the water in the water supply for the state of Illinois. So the water, what type of water it is and what it contains, like the amount of other chemical substances in the water. So it is for the prediction of those characteristics from other characteristics. So this is a data-driven approach, which uses our machine learning to predict the water characteristics. Means we will be using our data to drive our project and use that data to make decisions and do all of drive our decisions and drive our project. So in the next slide, please. So why do you need to make this prediction? So we need, in order to ensure the efficient and safe water supply, so we have to do the prediction, because the data may be determined by the lab tests and others, but simply relying on lab tests may not be efficient or safe, because it may be quite late by the time we get our results, and it's also for the more efficient, because if you have a way of predicting some of the characteristics, then the water treatment plant may be able to do some preemptive intervention on the behalf for the water, in order to treat it before it gets like unsafe to drink or something. And then it also has for the more efficient water, because if it may be too late, we may have to, for example, interrupt the water supply, so it decreases the efficiency. So in order to ensure more efficient water supply, we need to do this prediction, and that may be because the supply chain may contain many other chemical compounds like organic phosphorus, sulfates, ammonia, which are determined by lab tests. And then sometimes we need to prevent for preemptive intervention, like I already told you, and because there may be delay in the tests. Next slide, please. So what are these characteristics? The characteristics we are going to work on are these. There are total solids, which are the total solids dissolved in the water. There are suspended solids, or SS. There is 5-day biological oxygen demand, called BOD5. There is ammonia, content NH3, organic phosphorus PORG, total phosphorus called PTOT, sulfates called SO4, total Zindal nitrogen called TKN. And if you want to know what Zindal nitrogen is, I'll leave the link in the description, and I will leave in the in the description, and maybe I will just send a link to the chat to those who are joining here, and those who are joining watching us from YouTube. I'm going to leave the link in the description, so so that we can understand what Zindal nitrogen is if we are interested. The next next is PRCP NOA, which is NOA precipitation. So next slide, please. Yeah. So where do you get this data to drive our project? This data is maintained by Illinois Water Environment Association, who have done lab tests and maintain this data from every year from January 1st of 2001 to, and we have data until the last of 2018. Next slide, please. So here, this is the sample of our data, and there are some columns like those water characteristics we have already here, and here is by the date, and you can see some of the data are missing too. So we have to treat it like this, and so how it is going to be treated, I'll explain further. Next slide, please. Next. Yeah. So for first we have to do data cleaning. So there are a lot of, we can see that there is a lot of missing values in our data, and for that we have to do cleaning by, we have to fill in the data and something. And since we cannot work with missing values, they may need to be filled with revisionable values, or think of some other ways to do this. So, but if there are too many values missing in some of the columns, like you saw in SO4, there is too many values are missing. So becomes the prediction based on it becomes unreliable. So we do not really fill in the data for columns, and we rely on other methods that I'm going to explain later. Next slide, please. So here we can see how much data is missing for each column. So for some like BOD5, it's a little bit higher, but it's still tolerable. Other have quite low and manageable. But SO4 is too high, like almost 85% is missing. So we have to use another method for the treatment. So next slide, please. So how we fill our data, we use except for SO4, the method we are going to using to fill our data is something called linear interpolation. In the linear interpolation, what linear interpolation does is it fills in the data with evenly spaced values. So it also makes evenly spaced values, means it makes an assumption that like measure values just changes linearly over a short time. In the short time, the data is just changing linearly. So unlike other data like forward filling or backward filling, there's no sudden jump. So there's no constant and sudden jump, but it makes a linear, just goes a more smooth linear flow. And so if you want to know more about linear interpolation, here is a video that here is the video link, which if you want to watch it, like I will leave in the description, and for those who are joining here, I will leave in the chat. So the next one, please. Next slide, please. So for that we'll have to do feature selection, like for prediction, which feature to select for which target, which level. So so for feature selection, we are going to use what's called the covariance matrix. So to use any feature as a predictor of other, we select those with at least some moderate correlation. That means if there is no correlation at all, not even a moderate correlation, we are not going to select those features. So we set the correlation threshold of at least plus minus 0.3 in our predictor. And then okay, here is one question to others who are not our group. So why do you not restrict those features with only those who have a strong correlation? Anyone from not sure, any guests who are joining here? Okay, that's because like if there is a strong linear correlation, we see a strong covariance, but covariance doesn't really predict non-linear correlation that well. So So for that, to account for that, for non-linear correlation, we also use moderate correlation. So we just set the threshold of 0.3. So after feature scaling, we have to construct covariance matrix. And why do you need feature scaling in covariance matrix? Always, it's because otherwise we can't really get the covariance between 0 and 1. That's what we are desiring. Because to get covariance between 0 and 1, they have to be scaled down to the same feature. Otherwise, the bigger feature, bigger values will dominate. So if the correlation is close to 0, so if covariance is close to 0, we assume that the effect of that feature on the target is minimal. Next slide, please. So this is how what we got by this by plotting our covariance, right? And we can see there are some darker colors means there is deeper correlation, and the lighter correlation means there is less correlation. So this is based on this covariance matrix. We select our features. Next slide, please. So what about SFO? Like we I just mentioned that SFO we are not going to use, but we are not going to fill in data by linear interpolation, because the assumption, if there are too many data missing, this just filling in using speculative data is not a very wise idea. So we have very few data for SO4 to act as labels. But here is the thing: we have a lot of unlabeled instances. That means there are a lot of data where SO4 is missing, but there are data for other things. So what you can use is, what you can try using, what we have tried using is, we tried semi-supervised learning by using k-means. So what we are going to do is, next is we are using clustering by k-means. So no, previous slide, yeah. K-means means it's a popular clustering algorithm, as we have already known, and it assumes that all clusters are convex, and it assigns its point to the nearest cluster center. So whenever we are getting data point, which cluster it belongs to will be the nearest the data center, and it must be feature scaled. Otherwise, you know why it happens, because small data value means the Euclidean distance will be less, and the proportionally they will be out dominated by higher distance, higher value features. So even those may be high, they will be considered from the same cluster. So it doesn't really work without feature scaling. And what you can now do is use k-means to project our features, our data samples, into a k-dimensional features. That means if we do clustering using k features, say let's say 50 features, then we can convert each data sample into 50 feature data, and that is space, that feature is called what we call the cluster distance space. In cluster distance space, each feature is the distance to each of the clusters. Like there are 50 clusters, like in cluster, and so those 50 features of this data that we will be using will be the distance to 50 clusters. Now what we actually have is the data we are going to train will be only as much as there is SO4, because whichever we have SO4, we'll use only those data to train, but it will have there will be higher dimension data. So next slide, please. So next, I've also worked for deep learning. So I actually built one single function which does everything with deep learning, because it displays the data, trains, tests, and gives the results. So the thing is, we have used fully connected layer. Why not other type of deep learning? So I will talk about why I use fully connected layers later on. But okay, what we actually have is, we have two hidden layers, and I haven't changed the feature selection. The same feature I selected by covariance matrix, I have used the same. Previous slide, please. Okay. And I have built that for both classification and regression graphs. And we are going to we'll discuss why we use classification for NOA precipitation later on. But so the activation function we have used is called ReLU, which is by default. And then for outputs will be, for classification, it is softmax. For multi-class classification, it's softmax. For binary classification, it's sigmoid. And for regression, it's linear. linear output function because that just goes linearly. Next slide, please. So the cross function we have used is something called sparse categorical cross entropy. For multi-class classification, we use sparse categorical cross entropy. For binary classification, we use binary cross entropy, and for regression, there is mean squared error. And you may be wondering why there is both multi-class classification and binary classification when we are just classifying one thing. But the reason why is it will be explained later, like because we have our reasons for that. So why would you use for multi-class classification? Why is it is called sparse categorical cross entropy, not categorical cross entropy? What is the difference? The thing is, sparse categorical cross entropy is actually categorical cross entropy is actually used for something called one-hot encoding, in which the same sample may belong to different classes. It is more like, does this belong to this class or not? Does it belong to this class or not? So it may be same class, may not belong to any class, or may belong to more than one class. So for any it has to belong to exactly one class, but we use like class labels are numbers like 0, 1, 2. We use sparsity categorical cross entropy. For categorical cross entropy, it will be one-hot encoding type of data. So we use deep learning with fully connected dense layers, and some people have suggested to me use convolutional neural network, CNN. So why don't you use CNN? Well, CNN actually is very good for image classification because it can detect the features, image features like ages and others, but and working with some proxy the pixels which have on proximity to each other. But since we don't know which features are supposed to be closer to each other or farther to each other, because we don't know such relationship here, so convolution doesn't really work because you don't really know how they are related in many different ways. So for SO4 we have this higher wider hidden layer because it has more intuitive features also. And so if you want to learn more about deep learning or convolution, that I will also recommend one video from, this is actually my favorite YouTube channel for math, which I'll leave the link in the description also. From next one, my friend Subramanya, he will be explaining the rest. Thank you. I'm going to pass on to him.
Hi everyone, this is Subramaniam, and I'm going to explain. Can you move? Yeah. I'm going to explain why we are doing feature scaling for water data set. Before explaining that, I'm going to explain how uh, we the plot here. We can see I have built this plot by using data.plot for the different datas from initial date to final date, as mentioned in the dataset. If you see here, there are various differences between the features. Like for perceptron NOAA, we have a large distribution with a lower value, whereas for total solids, we have higher values and lower distribution. And there are also many differences between different feature. I mean scaling differences. If we train and test the model without scaling the data, then the regularization may ignore one of the feature because one feature might dominate the other one. So that is the reason we are using feature scale. We do feature scaling by using the scaling dot transform function. And as Manish explained, it is also used in covariance matrix, for which we change into the scale like 0 to 1, which we have used to get best set of features. Can you move to next slide? Yeah, and we are also going to implement linear regression model in the features. So first of all, I'm going to explain what is linear regression. The linear regression model is to determine the linear function between two variables. That is for lower dimension. If it is lower dimension, then it is between two variables. or else if it is higher dimension, then it might be between vector of variables and the y. So y is nothing but dependent variable. So linear regression assumes that dependent variable can be calculated by using linear combinations of x values. And can you move to the next slide? So I have explained what is linear regression, and linear here I have plotted this thing by using SNS.pairplot for entire data set, which is used uh, to plot the data points between each and every feature. Uh, Here, if you see, can you move a little upward? All these things. Yeah, this thing. If you see between ORGN and 3N, it's like that. If yeah, if you see between ORGN and TKN, the data is linear. That means as TKN increases, ORGN values are also increasing, which shows there is a linear correlation between them. In this way, there are linear correlation between some features. So we want to try how linear work regression is going to work on these features. That is the reason we are going to use linear regression. And can you move to the next slide? Yeah. Uh, yeah. I also done I also run different models on total solids features and SS. So first, after scaling is done for the data, by using covariance matrix with the minimum threshold covariance of 25%, we are going to select the best set of features for each feature. So after selecting the best set of features, we use best set of features as x variable, that is feature data, and y that is total solid. It depends on the variable, that is target variable. If we are doing for total solid will be the target variable. Then we consider different models, and each and every model is suggested by our my team members. I have suggested linear regression. Can you move to the next slide? So after running each and every model with the help of k-fold cross validation, which is done for hyperparameter tuning. It divides into different folds and get R2 square of, R2 score of each values, and we can find mean R2 with the help of k-fold. And after finding that, we'll compare R2 score for each and every model. So the model which is having higher R2 will be the best model. In the left plot, we can see that neural network is acting as a good model for total solids, and the right one is for SS. For SS, gradient boosting is acting as a good model. We also know that neural network is a combination of different regression models, linear regression models, and it is used to find complex patterns. Can you move to the next slide? Yeah. After getting the best model, we'll try and test the data with the best model we get. After getting that model, we'll plot the graph between true and predicted value, that is actual and predicted value. If you these two plots are for total solids and SS. Here the red line is for actual value, and blue line is the one with the predicted. That is our model, our base model. You can see there might be difference between values, but the predicted one is following the same pattern, almost same pattern with the actual one. So this is our model, and from here my friend Sai Krishna will explain.
Could you move to the next slide, Bhaskar? Yeah, good evening, everyone. These are the machine learning models that we have used to train our features. They are linear regression, ridge regression, lasso, elastic, net regression, random forest gradient boosting, and neural networks. If you see that we are using the first four are from the regression. This is because, as earlier said by one of my teammates, Subramaniam, he has explained about the pair plot, and he has shown the plot that shows that most of the data is linear. So if you can see that as the data is linear, so we are going to use regression. And if we take the next two, there is a ridge lasso and elastic. The linear regression is for the linear data. So for regularization, we have used ridge and lasso. Ridge lasso we can use for L1 and ridge for L2. The next one is elastic, random forest and gradient boosting and networks. And gradient boosting is been suggested by me. Could you move to the next slide? So gradient boosting. Gradient boosting is one of the most important method model that we use to train the features. Actually, gradient boosting is more better than random forest. It is slightly different. In random forest, all the trees are selected at once, but in the gradient boosting, each tree is selected additively. That is one after the one, one after one. So it can reduce the overall prediction error if you use gradient boosting, and it is slightly better than the random forest model. Could you move to the next slide, please? So if you can see the importance of gradient boosting, after training the features with all the different models that I have said earlier, the mean absolute error, we have used three evaluation metrics, that is mean absolute error, root mean square error, and the R square values. We can see that the gradient boost model has performed well with more number of features. So the parameters that we have used in this are the n estimators, maximum depth, and minimum samples. And we have taken the n estimators as a standard value of 100. Could you move to the next slide, please? These two features have been considered, the BOD5 and NSP. The feature selection is done by using correlation, and splitting of data is used by function train and for test and response split. And we have used 0.2% of our data for testing. We have considered different models using k-fold cross validation, that is value of cross validation to build a good model and to prevent underfitting or the overfitting. We have compared R2 scores to get the best model. That the model with the highest R square value will be a better model compared to the other. And we will be training and testing with the best model, plot the graphs between the actual value and the predicted value. Could you move to the next slide? Could you move to the next slide, Bhaskar?
Just a second, I'm facing some technical issue.
Oh, okay. Uh, so these are the R square value for the feature NF3. You could see that for the above feature, we could conclude that the R square value is highest when trained with random forest model. After performing with all the different models such as neural network, gradient boosting, random forest, and four types of regression, we could see that random forest has performed well for the feature ammonia. Could you move to the next slide? Similarly, for the BOD5, after training with all the different models, we could see that the lasso regression model has performed well in it and scored and got the highest R squared value in the case of BOD5. And as told earlier by one of my teammates, Manish, the BOD5 has considerably more amount of missing data than other things, and also SO4 has the highest of that. So BOD, in case of BOD, we got that lasso regression has the highest R squared value. Could you move to the next slide? As you can see, the evaluation matrix for BOD5 and NS3. The evaluation matrix for BOD5 is that we got mean absolute error as 19.87 and mean square error as 128.53 and R2 square as 0.58. And coming to the NH3, we got mean absolute error as 0.27, mean square error as 1.18, and R2 square as 0.95. The R2 score in the case of NH3 is slightly higher, and we got this the R2 score. The best model for this is random forest. Could you go to the next slide? As you could see the feature importance, you could see that for NH3, the TKN has the highest value for the feature importance for predicting the target variable as NH3. So our target variable is NH3 and the TKN has the highest feature importance for this. Could you move to the next slide? And also the feature importance for predicting the target variable as BOD5, we got P dot as the highest value. So this can also be explained from the pay plot also. Thank you. And from here on, one of my friend will be continuing.
Hi, this is Jashwant Chaudhary. So I'm going to say about the random forest regressor. So it is the one of the model which we use it for to predict the future score for the all the features which is in the data. Random forest is a meta estimator used for prediction to get more accurate prediction. So in this diagram shows the structure of a random forest. So for example, if we given the sample input, sure, and it divides into several decision tree and some prediction values and the calculate the average of all prediction values, and it comes as a random forest prediction. And also random forest is used for like our fitting problem in the distance tree and the less the variance to improve the accuracy. Can you go for the next slide? Okay. So here I'm going to say about the k-fold cross validation. So we have used the 5-fold cross validation to avoid overfitting and underfitting. Can we predict the most accurate? So a k-fold validation is mainly used for evaluating the model performance. So k-fold gives more stable result since training and testing is performed in several database. So in this figure, it shows the structure of cross validation. For example, here we split into the training and data sets, which choose a k-1 folds as the training data sets. A remaining folds is for the validation, and the k length should be less than actual length of the data set of every iterator of across cross validation. Must train a new model than previous trained model. So iteration will done k times k-fold model makes the best accurate prediction. So next slide. So I'm gonna say about the TKN future. So TKN has the good correlation with the other futures in the water data set. So in this picture, you can see like TKN has a good relation with the total solids and the SSN BOD. Like total solids is 0.35 and for the SSN 0.57. And with the overall futures, with it has the more good correlation. So with other futures, and also in the below graph shows the R2 square of TKN. Out of all model, ridge regression is the best R2 score for the TKN. And the next slide. So here in the left side first graph shows that red dotted line is the actual values and the purple one are predicted values. So you can see in this most of the cases all predicted well. In some cases there are some errors, so it shows some not predicted correctly, and the same as the below diagram. So it calculates the predicted values correctly. So some of the cases the error values is predicted. So in the future importance, TKN mostly correlated with the total phosphorus future compared to another one. On the next slide. Next slide, previous slide. Previous slide. Can go previous. Yeah. So in a SO4, there are a lot of data is missing. So coming to the SO4 future, in this future we have more unlabeled data compared to all other futures. So predicting become more tough for unlabeled data. But we filled the unlabeled data with clustering. Those 50 futures come from the clustering. So the claiming clustering is the project each label data to point the cluster distance space. Next slide, please. So in this R2 square, in this graph, R2 square is shown for the SO4. So here the lasso regression shows that R2 square is more accurate than all other models. But the evenly grade boosting is also shows the same as the lasso. So we took the lasso regression, a slight difference. And the below diagram shows that red dotted lines are actual lines, and the pink one are the predicted ones. So if you see in here, like in the below graph, red dotted lines shows the actual, and here it shows the so much different. So that's it. Next slide is gonna say, my friends.
Yeah. Hi all. Good evening. So this is Bhaskar. So coming to the next feature, that is precipitation envoy. So this precipitation envoy feature in the water data set is completely different. So basically this feature has a no empty values, and it does not correlate it with the any feature in the water data set. So, and if you see the left hand side image, the correlation plot diagram, so which was highlighted in the yellow color. So there is a correlationship, the precipitation correlationship with the other features. So if you see the correlation, it is all negative and minimal. So that's why it has a, and this data is also a bad data. So if you see the right hand side plot diagram, so see the right hand side plot diagram also, nearly this feature contains 5000 zero values, and it suddenly goes to high range, that is 6.86. So that's why we converted this task into a classification task and used all the features for this feature prediction. So, and the next question is like, how I need to fill this feature data, because this data is already filled. So again, we are going to fill this feature data. So how we are going to fill? So that we are talking about in this slide. So in total 100% of data, so we will now divide the bottom 90% of data into two different classes, and top 10% of data will be a class of its own. So in other words, can I tell us like if we take as a complete 100% of data, in the top 10% of data, it should be a 0.32, which will be assigned as a 2 in the top 10%. And the remaining bottom of the 90% of data will be assigned as a 0, 0 and the 1. Like from 0 to 0.6 threshold will be assigned as a, all the rows should be assigned as a 0, and the remaining 0.16 to the 0.3199 will be assigned as a 1. So we divided this data set into a 3 classes, that is 0, 1, 2. So if you see this diagram, we just assign the 0, 1, 2 values to this feature data set, that is precipitation NWA. So coming to the next slide, can you move to next slide? Yeah. So I already told that we are converted this task into a classification. So, and what about the classification models? So in this feature prediction, we used the 6 classification models. So those are logistic regression and decision tree classifier and support vector mission and ADA boost classifier and random forest and gradient boost classifier. So basically, we used the similar classification models for the above regression models, which is used for the other features. All the regression models, whatever used for the other features, we just used the classification models of that same. So basically, if you see the next slide, can you move to next slide? Yeah. So after using the all the models, so this is the plot diagram which has show the all the accuracy scores of the each different classification model. So in this out of 6, the best model one is the gradient boosting classifier. So and the right hand side image is the feature importance of that feature. Like the first one is the total solids, and the second one is the SS, and the third one is the BOD5. So can you move to next slide? Okay. So if you see this slide, this is the classification report for that the highest the one report, that is the gradient boosting classifier. So for if you see that this classification report, it not performing well, because if you see the class 0, it's performing good, like for it has highest score like precision and recall 0.86 and 0.97. But if you see for the class 1 and class 2, it is very low. That means it's not able to classify the class 1 and class 2, because it has the identifying all the values as a 0 only. So, and if you see the right hand side our classification report, this is a classification for the classification precipitation via deep learning method. So in that case also, it is not performing well. So and it has a very poor predictive performance from the other feature, because it classifies all them. I already told you, it classifies all them as a 0. So because we cannot predict the other classes because of the high number of zeros which are having in that class 0. So in that cases, we modified some little bit of that the threshold into a top 5%. So in that case also, we can see like how it behaves. So can you move to next slide? Yeah. So we just modified as a threshold. Before it was a threshold as a 10%, top 10%. Now we change it as a threshold into a 5%. That means the top 5% will be as a one class, and the remaining 95% will be a one class. So top 5% will be treated as a class 1, and the remaining 95% of the data will be treated as a class 0. So in that case also, it not performs well. If you see the left hand side classification report, the class 0 precision and recall is very high, and if you see the class 1 precision recall, it is very minimal. So if you see the right hand side of the classification report via deep learning also, it is very minimal. So what I conclude was it was predicting almost all them as a 0 and identifying only once in the prediction. So because of that, there is no much trained data, and more anomalous data only. This was the not performing well. So we can conclude this as a not working feature. And so basically, we did not leave the feature. We tried our best to get the correlation with the other features, but because of the anomalous data and the minimalist data of zeros and one, it not performs well. So I'm handovering this to next person.
Yeah, am I audible now? Yeah, I'm sorry to interrupt that. Yeah, myself Ashok Kumar. I'm here explaining two features in this project. That one is ORGN and PTOT. Coming to ORGN, these are the features having a good relationship. As we know, these total solids, SS, NH3, TKN, these are good correlations with the ORGN. In this, I plotted that future in the matrix values. These are the as we seen in this image 0.49, 0.77, 0.371, 0.81. And coming to perceptron, that negative value that is not correlated with the ORGN, and there is a high correlation with ORGN is 1. That value is shown in this picture. Can you change sec? In this ORGN, these are the models we use to implement those things. That was linear regression, lasso regression, ridge regression, and elastic net regression, random forest, and gradient boosting. When we are implementing these all models, we got a best model. That one will be. Can you change this slide? I'm sorry. That one is in the gradient boosting. We got in the best model for this project. When we are implementing ORGN, this gradient boosting value is to compare all models. The mean absolute score is too high. Can you change the slide? Yeah, as I said that after I'm implementing all models, and I got these gradient boosting is high. That is ridge regression performs more good than that. As we seen in that r squared value, it's showing clearly ridge regression is very high. And after tuning this after tuning and that model, we got this regression in that mean absolute error is 0.26 and mean square error 2.922 and R2 score is 0.91. This is the actual values and predicted values. Actual values are very low because of as we implemented in this anomalous data to predict little bit predicted values is more than actual value. Coming to next slide. As we implemented same as like ORG and PTOT also. Here we seen in PTOT the total solids will be 0.42. These features are correlated with the PTOT, and SS also is a good correlation with PTOT as we seen in this matrix 0.72, 0.8, 0.66. There is the only negative value PRCP that is not correlated with the PTOT. Can you change the slide, please? Yeah, this is the coming to the after we implementing same like ORG and PTOT also we implementing 6 models, and this is the best model for PTOT. And gradient boosting is getting a good R2 score. That is as we seen in the graph, these R square value. Next slide. Yeah, after tuning the parameters, we get this mean absolute error and mean square error. R2 score is 0.88. As we seen in this graph, predicted values and true values is almost we are thinking like predicted is more compared to actual values as almost same. Yeah, come. Thank you. We are concluding. We are open for doubts. If you have any questions, feel free to ask. And my friend will show the demo.
Okay, I'm going to share my screen.
Our project automatically generates the reports and the graphs and the visualizations for our project, and we just go and run for just go to runtime and yeah, runtime and please Google. Oh, no, click runtime. That click restart and run all. Yeah, it takes some time and then wait, don't do that. Okay, we can actually go and we can actually show that this actually generate a report, and I can actually show, like, let me share my screen, please. Okay, Bhaskar, let me share my screen, please. For my laptop one, not this my phone one. This laptop one, not that one without camera. No. That Manish.
Yeah, you can share your screen.
Okay. No, it is still doesn't. It is still doesn't allow.
You can.
I guess Subramaniam has to stop sharing so that you could start sharing.
Okay. You stop sharing my screen. Okay, I'm going to share my screen and here. No, I can still not share. That Manish is from the laptop one. Yes, we have actually two slides, and I can show the one in the process of execution and another which has already been executed. So for the demonstration, yeah.
Share my screen.
Okay, I can share my screen now. I can share my screen.
You can take my.
Okay. Here is our one of the growth, and this is actually running, and I can show you in real time how it is generating a report. For instance, it has now, like, it has already generated report for others, like, and now here, like, it's moving, and uh, where is it now? It's the report is being generated, and also, like we have said, it is like the longest time it is taking is like for this random grid search for the hyperparameter tuning, and this is the part of, after we select the best model, we do hyperparameter tuning, and it is taking some time to do that, and yes, because, and it is tuning in real time, and in the real time we can show that it can take, it can show the best params and then generate our graphs. And to show the already run one, which in which there are already graphs generated, I'll let my friend Subramaniam do the part of screen sharing. So at this point, I'll I am look, this the ones being shared, and he will show the already one. He will show the one which has already run and has generated all the graphs.
Yeah, here you can see that we have run each and every model for every feature. So I'm going to show the output. So this is for best feature selection. Just a moment. Yeah, you can see here total solids. Yeah, for total solids features, we have done training and testing. After doing that, we have done K4. Then we have run several different regression models. From that regression models, we'll select the best one. And after selecting the so these are the different metrics for that thing. You can see mean absolute score for each and every model on total solids. If you see here, we get neural network auto score is high. We are using that. In the same way, we are doing for all the features. So after getting the best model, we will train and test with the best model on the total solids data. And we were plotting a graph between true actual values and predicted value. You can see that here. From here, Manish will explain.
I guess your mic is off, Manish. Is he audible to you?
Sorry, I was mute. Yeah, there was here we are using deep learning model to train and test regression. What this does is this function actually calls everything. It generates the it splits the training data, does testing, training, and everything, and then generates the all the reports. So here it is being reported, and similarly, the same thing what we were doing before, it will be generated similarly for other models like for SS. Same generated, it is being generated in the same way, and in the same way it is also using some deep learning model at the in the end. Using deep learning model for that, and using it also has got its own value and RT scores, and the similarly the same it has selected a feature, and then by using the comparison of different metrics, it has chosen the best feature, and then it uses the model for hyperparameter tuning. Similarly, it goes for other, and similarly, and finally uses uh, deep learning. So we have actually used deep learning for a few models, and those who were used early on here where you use deep learning for all the models all at once. Here. Mm, all at once, and this is actually we used linear more we used uh, a deep learning for the linear regression all at once, and then their values were used later. So this is the value that we are using rather than the one that was used down below here, in which it calls it calls, and then it with the function returns all our evaluation scores, and those evaluation scores are kept in the are kept here, which is used down below. Mm, Finally, in that way, our report is being generated using deep learning similarly, and we use the similar features for all the features. We have the similar workflow for all the features. Finally, for SO4, we use the data which is in the feature uh, in the cluster distance space. We use similar 50 we use 50 data sets for cluster distance space. Those 50 featured cluster distance space. Similarly, we also use, but for that we use wider neural networks with about 50 and 20 neurons. Uh, And finally, after generation of all the reports, we also worked for NOA precipitation, which is we are using classification tasks and calculating its confusion matrix and F1 score, all at usual. Mm, Here, here the confusion matrix is being generated for our predictive model, some by our system. And here's the contrary matrix. For example, for 0 and 0 it's 1058. For those for those 0 which is predicted as 1 is 3, and those 0 is predicted as 2 is 38. And then there is 75 of 1 predicted as 0, and 101 of 2 predicted, or 101 of 2 which is predicted as 0. And then none were being predicted as to 1, but 6 of 2 were being predicted as 0. So yes, it did not perform well as we did not actually work well for the classification as we had hoped. But yes, and it is how we evaluated it by using confusion matrix and F1 score, precision, and recall for 0 and 1. So here is our demo, and if you have any questions, you can ask, please. Anyone? I think there's only one. Okay, I think we have anything else? This is the end of our presentation, and have a good day. We are ending our session. So thank you. Merry Christmas. Yeah, Happy Christmas, anyone. Thank you, everyone.
Thank you all.